Let's have a look on the second example. A steel beam ABC with a uniformly distributed load along AB and a concentrated load at point A. The beam is built in at point A, pin supported at point B, and pin roller supported at point C. The Young modulus and the second moment of area is 200 gigapascal and 10 times 10 power 5 millimeter power 4 respectively. By using the finite element methods, so we would like to determine the unknown degree of freedoms, calculate the reaction load and the moment at A, and lastly to calculate the bending moment at the midspan of AB. The first step that we have to do is to sketch the model or to draw the free body diagram and to determine the degree of freedom at each point. So in this case, we have point A, B, and C. So we have to draw the layout of the beam ABC. Then we determine the degree of freedom for each of the nodes. For example, for node A, we know that this node has been built in, so it cannot move in Y direction, as well as it cannot rotate. That's why we have VA equal to 0 and the theta A equal to 0. While point B is a pin supported, so meaning that it can't move in Y direction, but it still can rotate. And for the point C is pin roller supported. So the keyword here is a pin support. So when pin, it still can rotate, and at the same time as it has roller in Y direction, so it can move in Y direction. So in this case, VC is unknown, theta C also unknowns. So we have two elements, element 1 and element 2. Element 1 is between A and B. Element 2 is between B and C. So total degree of freedom is 3. The second step, we have to obtain the stiffness metric for each element. For that reason, we have to refer back to our free body diagram as well as our K matrix for beam. And we know that in this case, the I is given, which is 1 times 10 power negative 6 meter power 4. And the modulus Young for element 1 and element 2 is the same, as they are made from the same material, which is 200 times 10 power 9. For the first element, we have to check in our free body diagram. We know that VA, theta A, and VB is equal to 0. Thus, in this metric for element 1, we can eliminate the VA, theta A, and VB from the beginning. So we just need to fill up the column for theta B according to the matrix, the formula given. And then we have to solve the front part here and multiply to this value in this matrix. And we obtain the value as shown in the slide. For the second element, element 2 is between node B and C, and in this case, only VB is 0, and the rest is unknown. For our matrix, we just need to eliminate VB. And the rest column, we just need to refer back to this matrix and fill up all those values. And we solve the front part and multiply to those values inside this matrix. And we obtain the values as shown in the slide. The third step is to obtain the global stiffness metric for the whole structure. For this step, we have to refer back to our K matrix for each element, and then we have to insert this matrix into the global matrix. For example, a matrix 1 is started from theta B and VA. Okay, so the value is 300. So we check theta B and VA, the value is 300. And the second value, theta B and theta A, which is 200. So we check theta B, theta A, the value is 200. And we insert for the rest of the value until theta B and theta B, which is 400. Next, we have to insert the K2, which I put in the blue color to differentiate from the first element. So in this matrix, it starts from 300, which is theta B and VB. So we check theta B and VB. The value is 300, and followed by theta B and theta B, 400. Check theta B and theta B here, the position 400, and we do the rest according to this notation here. Okay, so for the last value, for example, theta C and theta C, so we check theta C and theta C, so the value will be 400. Next, we just need to get the summation of those values inside the matrix so that we can have the global stiffness matrix for the whole structure. The next step is to apply the boundary condition, as we know that VA, theta A and VB is equal to 0. So we have to eliminate the row for VA, theta A and VB so that we can obtain the reduced K matrix for the next step. Before we can proceed with the system linear equation, in this problem, it been applied with a distributed loads at between point A and point B. So the next step, we have to get the equivalent nodes at point A and point B. For that reason, we have to use these equations, okay, and then we have to apply element by element. So for element 1 is between A and B. Okay, so according to this value, P in this case is equal to negative 10 kilo Newton per meter. And L for element 1 is 2 meter. So just use this equation. Replace P with negative 10, L with 2, divide by 2, then we obtain 10. And this is for vertical force at AY. The second value here is the value for the moment at point A. And then the third value here is for FBY, the vertical force at point B. And the last one is the value moment at point B. Okay, so next we can obtain the F total for each point. So at each point, we should have vertical force and moment. For example, in this case, at point A, we have negative 10 and negative 3.33 for moment. At point B, coming from this value, so we have 10, negative 10, and moment 3.33. While at point C, we have a applied load. Okay, the direction is downward, so the value should be negative 2. And at point C, we do not have any applied moment at this point. So the moment should be 0. So we can represent all this value, okay, into our free body diagram, something like this. But please note that at point A, as it has been fixed joint, so thus it will have a reaction force in y direction as well as moment reaction, as this is a fixed joint. While at point B, it's a pin supported, so it only has reaction in y direction. Once we have solved the equivalent force as well as the global stiffness matrix, then we can set up our system linear equation, which is F equal to KU. And we can set up, for example, F, in this case, our unknown is theta B. So in this case, theta B, so we have to recheck in theta B is related to moment MB. So that's why we use 3.3. And then for VC, okay, so the relevant value should be the vertical force at point C. And the last one, theta C, it should relevant to moment at point C. That's why it's equal to 0. So the next step, just need to press your calculator to obtain the unknown degree of freedom as shown in this slide. If we want to calculate or determine the reaction force and moment, for example at point A, as we have reaction in y direction and reaction moment, we have to refer back to our global stiffness method. And remember that our SLE is F equal to K times U. Okay, so for example, if we want to solve for reaction vertical force at A, so we have to refer back to rho VA. So here we should have our F here equal. So our F, refer back to point A, we have negative 10 plus RF AY. So by taking out this equation, so we can get our first equation to solve for reaction FAY. Okay, so here we have negative 10 on the left side, negative 10 plus RFAY equal 300 times theta B. So that's what we have here on the right side. Y for the moment, okay, we have to refer for the rho for theta A. So in theta A, remember on the F side, okay, on the F, we have negative from the free body diagram here. We have negative 3.33 plus RMA equal to, on the right side, which is 200 times theta B. So that's why we have obtained this equation. So that we have only have one unknown here. So we can solve for reaction moment as well as reaction in y directions at point A. If we would like to determine the bending moment at the midspan of AB, which is somewhere here in the middle, okay, so we have to refer back to those values that we have calculated before. For example, at point A, we know that VA equal to 0, theta A equal to 0. At point B, VB equal to 0, and theta B, we have a value. And please remember that for natural coordinates, it's always start with negative 1 and ended with 1. So in this case, as we like to know the value at the midspan in the middle, so we just need to refer or need to calculate or to determine the natural coordinate at the middle. So of course, when it will be in the middle, so zeta will be 0. Okay, if somewhere here, I would say the zeta equal to negative 0.5. At this point, zeta equal to 0.5. So in the middle, zeta will be equal to 0. Next, we have to refer to the moment equations. Okay, and then it must be according to the element 1, where we have VA theta A and VB theta B. If you look on this equation, we have 4 terms: 1, 2, 3, and 4. So it's always for the unknowns or the degree of freedom in one element. So we always have V theta, V theta for first node, and this one for the second node. Okay, this is the first node. For example, in this case, it's node A, and this one is for node B. Next, we have to check in this equation. We know that VA is equal to 0, and as we would like to calculate the value in the middle, okay, zeta also equal to 0. So in this case, we can eliminate the first term as VA equal to 0, theta equal to 0. For the second term, we know that zeta is equal to 0, we can eliminate, as well as theta A also equal to 0. So the first and second term, all these values are 0. On the third term, we check third term VB is equal to 0. So again, for the third term, we also can cancel it, as this value is equal to 0. And the last one is only zeta is equal to 0, but we still have this value 1 multiplied with theta b. So theta b in this case is non-zero. So we can calculate, put the value of theta b into this equation, and we just need to solve the first part here. And next, we can determine for the moment at the midspan of AB. So the value will be negative 167 Newton meter.